Everything is made of patterns. Have you ever noticed that? Like take a seashell. There's a spiral inside that spiral inside that spiral. The spirals get tighter and tighter until you can't see them anymore. Now if you grab a piece of broccoli, look at that. What about the veins in a leaf, or the ridges on your fingers, or the ripple marks on the beach? Patterns, patterns, patterns. In this video, we're going to uncover the secret story behind these patterns. We're going to show you how they work and how they relate to each other. And we're going to tell you why we think everything is covered with patterns. It's coming up right now. First, we're going to take a look at some basic ideas that crop up again and again in nature. Then we'll show you how these ideas combine in complex ways to make new patterns. So pay close attention. In part 1, we'll cover Fibonacci in nature. In part 2, we'll cover the golden ratio. In part 3, we'll cover symmetry. In part 4, we'll cover fractals. In part 5, we'll cover spirals, storms, and galaxies. And in part 6, we'll try to answer why math shows up in nature. And in part 7, we'll talk about how we use nature's math. So let's start with a classic, the Fibonacci sequence. Here it is. 0, 1, 1, 2, 3, 5, 8, 13, 21. In this sequence, the first two numbers are 0 and 1, and every number after that is the sum of the two numbers before it. So to get the third number, you add the first two. To get the fourth number, you add the second and third. To get the fifth, you add the third and fourth, and so on. Now, the cool thing about this sequence is that it turns up again and again in nature. Take a look at the spirals in a sunflower. The number of spirals going clockwise and the number of spirals going counterclockwise are often consecutive Fibonacci numbers. Same with a pinecone or a pineapple. The spirals in these plants are actually an efficient way of packing in lots of seeds or fruits while making the most of available sunlight. So if you want to pack things in tightly and expose them to a lot of light, the Fibonacci pattern is the way to go. What else do we see in nature? How about the arrangement of leaves on a stem, or the petals on a flower, or the seeds in a honeycomb? Again, the Fibonacci sequence pops up. What about hurricanes and galaxies? Their spiral shapes also follow the Fibonacci sequence. Or take a look at your fingerprints. See that there's a Fibonacci spiral going on there too. But that's not all. Let's move on to the golden ratio. This is a number, roughly equal to 1.618. It's often found by dividing two consecutive numbers from the Fibonacci sequence. So we can write it like this. 1.618. But the golden ratio doesn't just sit around. It shows up in all kinds of places in nature. For example, the proportions of leaves, seashells, hurricanes, and galaxies often follow the golden ratio. It's the same in art, architecture, and aesthetic design. Check out the Parthenon in Greece. Its architect carefully arranged the columns according to the golden ratio. Same with the Mona Lisa, and even in everyday objects like cups or phones. Designers often use the golden ratio to make their products look balanced and appealing. But the golden ratio isn't just a matter of aesthetics, it has to do with efficiency. When you divide a line into two parts in the golden ratio, it turns out that the longer part divided by the smaller part is also 1.618. No matter how you slice it, the golden ratio is all about balance and proportion. Okay, now we're ready to move on to part 3, symmetry. Organisms across the animal kingdom exhibit different types of symmetry. Some are truly symmetrical, meaning they can be divided into two mirror images that are exactly alike. Others have radial symmetry, where they look the same from all sides. Still others don't have much symmetry at all. Symmetry often comes down to genetics. Most living things on Earth have bilateral symmetry, meaning they have two sides that are mirror images of each other. That's why we have two arms and legs, two eyes and nostrils. Symmetry helps organisms function properly. Having two eyes on the front of your head gives you binocular vision, which means you can judge distances more accurately. It's a big advantage when you're looking for food or trying to avoid being food. Of course, no organism is perfectly symmetrical. There are always small differences between the left side and the right side. For example, your heart is slightly tilted to the left and your stomach to the right. But these tiny differences help make each of us unique. Now, let's move on to part 4, fractals. Fractals are patterns that repeat on smaller and smaller scales. Take a look at this tree. A tree looks like a tree, a branch looks like a tree, a twig looks like a branch. That's an example of a fractal pattern. Fractals have three key properties. First, they're similar. The whole looks like the parts. Second, they're recursive, meaning the pattern repeats itself over and over again. Third, they're infinite in detail. If you zoom in on any part of a fractal, you'll find the same pattern you see in the whole. Fractals are super useful. They're an efficient way of packing complex shapes into small spaces. They also help distribute resources like water or nutrients in a fair and orderly way. So it's no surprise that fractals show up all over nature. Think about trees, rivers, lightning, Romanesco broccoli, blood vessels, coastlines, and even clouds. All these natural phenomena follow fractal patterns, and we humans have learned to take advantage of this. We use fractals in engineering, computer graphics, and financial modeling. In fact, Fractals have become famous in mathematics. Some of the most iconic fractal patterns include the Mandelbrot set and the Julia set. Next up, Part 5. Spirals, Storms, and Galaxies. Ready for a mind-blowing idea? The spiral in your toilet flush is the same as a hurricane, which is the same as a spiral galaxy. These spirals are called logarithmic spirals. They have a special property. They keep going forever in both directions. But what's really amazing is that these spirals are mathematically perfect for distributing energy. For example, hurricanes and tornadoes are vortices of awfulness, but they need to stay intact to cause maximum damage. The spiral shape lets them keep spinning without falling apart. Likewise, galaxies are huge collections of stars, gas, and dust held together by gravity. The spiral shape keeps everything from flying apart. Even your ear canals follow this spiral shape. It lets you capture sound waves and send them to your brain. So logarithmic spirals are all about balance and proportion. They're an efficient way of distributing energy and matter. Now it's time to tackle Part 6. Why does math show up in nature? Mathematicians and scientists have long been puzzled by this question. We know that nature uses math to build everything from seashells to galaxies. But why? Well, there are two main theories. First, math is a human invention. We use it to describe what we see in nature. Just because the universe happens to follow mathematical patterns doesn't mean those patterns exist independently of us. They're just a convenient way for us to understand the world. On the other hand, math could be a discovery. There's some kind of deeper truth to these patterns. The universe works like this, whether we're here to observe it or not. Physicist Eugene Wigner called this the unreasonable effectiveness of mathematics. Why should a human construct fit nature so well? Maybe it's because nature is built on math? The universe is made of math? Finally, Part 7. How we use nature's math. Humans have been taking inspiration from nature for thousands of years. We study the patterns in seashells and leaves to make better designs. We copy the strength of spider webs to create stronger materials. We imitate the flight of birds to build faster planes. In a field called biomimicry, engineers and designers look to nature for solutions to modern problems. Take the hummingbird. It can hover in midair by flapping its wings super fast. Engineers have built drones that can fly backwards and sideways the same way. They call them quadrotors. Another great example is Velcro. It was invented after a guy noticed burrs sticking to his clothes. He realized that if he could make tiny hooks and loops, he could create a fastener stronger than any button or zipper. We're also learning to use nature's patterns to teach computers. Neural networks are a type of artificial intelligence. They're inspired by the neurons in your brain. These networks can learn from data and improve their performance over time. So when we look to nature for inspiration, we're not just copying what we see. We're uncovering hidden patterns and principles that can help us solve problems in unexpected ways. So there you have it, the hidden math behind nature. We hope you enjoyed this journey through the patterns and principles that shape our world. Remember, everything is made of patterns. And if you look closely enough, you can see the beauty and order that underlies the chaos of everyday life. Thanks for watching. We'll see you next time.